Dear students, today we are going to discuss how to perform the experiment on fault analysis, transient stability and automatic generation control in power systems for Power System Lab 2. There are 5 parts for this experiment and you will be exposed to MATLAB or Octave, Simulink, Scilab and XCOS. Theoretical background of fault analysis, power system stability and AGC is part of the theory course Power System Operation and Control. For the first experiment on fault computations, you would require either MATLAB or Octave. So I would explain how you are going to install Octave. So you need to write download GNU Octave in a browser. So you can directly go here. Octave is available for Linux, Mac, Windows, all operating systems. If you have MATLAB, then you can easily run this code. However, if you do not have MATLAB or you are outside, you are in a system which do not have MATLAB access, then you can simply download Octave. It is a MATLAB clone. So click on here, download Octave installer. I have already downloaded it. Okay, so and I have installed it. So for running this code, the files have been uploaded in the link that is provided. So you can go to the GitHub page and you can find out there are 2 folders related to the 2 software experiments that you are going to perform in Power System Lab 2. The first one was discussed in an earlier video related to economic dispatch, load flow and optimal power flow. And for this experiment, which relates to fault analysis, transient stability computation and AGC, the code is available in this folder. The first code is related to UGPS Lab 2 question number 1. We are going now to open it in Octave. Okay. So we will clear the screen and we will go to the editor. I have already opened this. It is always better to put your code in a workspace and then open it from here. So as you can see here, my workspace is inside the document folder. I have used Octave WS and inside that I have put my code. Now this code simply shows you how to use computers for fault computations which are very involved. Before the computation of the fault, like symmetrical fault, line to ground, double line to ground, line to line, you need to compute the positive sequence, negative sequence and zero sequence networks of the system, which is shown in the manual and must have been covered in detail in your theory papers. So when I run this, all the related quantities are computed. Note here that if you are running this code in MATLAB, you need to replace this command lines by the MATLAB command line, otherwise it will show error. Next we will go to question number 2. So these are the details of the some details, only sample as provided further details you need to compute. Okay, the second question is related to the Z-bus formulation. As you know from your theory syllabus, Z-bus is required for systematic fault computations. It may not be always possible to go in detail of positive, negative and zero sequence networks. We can do or compute the fault capacity of a system by simply using Z-bus. So for a system, there are some steps which can be used for formulation of Z-bus, like type 1 modification, type 2 modification, type 3 and type 4 modification. Okay, and a program is created for that. So you can see this program here in the GitHub file, which is, you see, UG PSLab to Z-bus. Now this Z-bus program will utilize this data in the CSV file Z-bus line data. So for that, I will open this in Octave. As usual, you can also use MATLAB for this. So this code, this was an available code which was already available in the GitHub. I have modified it and you can use the function directly or make modifications in it. So this refers to Z-bus line data, which simply says about the configuration, like what are the line impedances which connect from one bus to another. So using this various modifications, this program computes the Z-bus. So before running that, we will clear the memory, then we will run this program. You see, the Z-bus is formulated. Now the advantage of this program is that you can take any system and simply change the data in the Excel or CSV file and you can formulate the Z-bus. Then the next part of this is simulating fault using Simulink, MATLAB Simulink. So for this you require access to MATLAB Simulink, which you can get from any laboratory computer. So what you do, so you need to add various blocks. Simply don't copy, just add various blocks, then go on to the blocks, change the fault simulation times. Okay, after the fault, you have simulated the faults, you check the scopes, okay, for voltages and currents. Okay, so this is the system I have obtained from, I have downloaded from the GitHub and I have opened it in MATLAB. So using run, I will run this. Okay, I am not changing anything. It is for you to explore different blocks and change. So once it is done, I can simply see the various waveforms, okay, by clicking on this VLIL scopes. Okay, fine. Okay, the next part is, the next part of this experiment is transient stability. And this is a question from the book and we will run this using Scilab. As you can see here, a sample solution is given. We are basically going to simulate these equations, which is step by step or point by point method solution of the swing equation, and we are going to get a curve like this. Okay, so for this we have to open Scilab. So prior to that, you might have installed Scilab in your last semester. So I'll show you how to install Scilab. So here write Scilab. It's a free tool, so we can download Scilab. So it takes some time to download this folder, and so I have downloaded this and installed it. Now I am going to open it. So this is the Scilab console. So again, I will suggest you must create a kind of a workspace for you to work. Okay, I have created the workspace. Okay, then using file open, you can go to the workspace, which you can put anywhere, and I will open this code UGPS lab to experiment number 5 stability. So this code is already available in the GitHub link. Now this is downloaded from cloud.scilab.in. After completing this, I will explain something about this cloud.scilab.in. So this is where this problem is solved. Okay, now let me show you the code. Okay, this is the code. So I will run this. So if I run this, I would see a curve like this. Okay, so this refers to the curve that we have seen in the manual related to, as you can see, the sustained fault clear at 2.5 cycles, fault clear at 6.25 cycles. Now when this code is run in the console itself, in the Scilab console, okay, so you can see the various curves, point by point method calculation of swing curve for sustained fault, for fault clear at 2.5 cycles, fault clear at 6.25 cycles. So here the details of how the delta swings is computed. So as you can see here the delta goes on increasing, that means it is unstable situation, whereas when fault is clear as 2.5 cycles, the maximum angle is somewhere as 33.975 degrees, whereas when it is 6.25 cycles, the maximum angle is 51.630 degrees, to which the generator goes. But again, it again comes back, and hence both last two situations are stable situations. Okay, so you need to attach this to your submissions. You are encouraged to experiment on this code. Now I will show you and explain more about this cloud.scilab.in. So let me go to, okay, so in this website what you can do is you can choose any category. Say I would choose electrical electronics engineering. Then you can choose any subject, suppose power systems. Then you can choose any textbook. Okay, so here this question was from chapter 12, power system stability, and here swing curves are actually sustained fault. Okay. So this code was downloaded from here, so you can directly execute here, but it will take some time. Otherwise you can run the code locally in your computer. Okay. So next we will go to our last experiment. The last experiment is related to the automatic generation control. Now here, as you know, the various parts of the system can be represented as control blocks. So there are 4 problems here. One is simple PID control simulation. Second is one single area system. Third one is single area system with various controllers. And the last one is a 2 area system having the following specification. Now for the single area system, such block diagram needs to be made. Okay, for all the systems the block diagram is required to be made. Okay, now remember that these blocks can be made in Simulink as well as in Scilab. In Scilab we will specifically follow Scilab here, because Simulink, if you have access to our laboratory computers, then you can use it in Simulink. However, if you have a different computer who do not have access to MATLAB, you can use XCOS. With Scilab it is downloaded. So we'll go to the Scilab folder. Okay, so here on the top of it, if you go here applications, when you click on applications, then there is XCOS. Okay, so when you click on XCOS, okay, when you click on XCOS, so such palette browser will be there and a blank file will be there. So we need to drag the blocks from the palette browser to this blank file and create blocks like this. Okay, so you need to do the block diagram for the PID controller, for the single area system model, okay, and with control single area PID controller, single area system model, PID controller with single area system with various controllers, and finally this 2 area system. And you need to obtain the response in the various scopes. Okay, here the scope and C scopes and clock signals are there. Okay, so this completes all the experiments, and as I'll repeat again, all this code is uploaded in this GitHub profile. So here you can see question number 1, question number 2 which is JetBus, question number 3 which is fault simulation using Simulink, question number 4 which is stability. However, the block diagrams are not created, because only when you create the block diagrams using the palette browser yourself, then only you can understand this XCOS as well as the concept behind block diagram creation. So with this, your experimentation is over. Then you need to write what you learned from this experiment, and these are the books that has been followed in creating this manual for this experiment. Thank you.